Okay, today I'm going to begin with the following. Do you remember about a year ago, you were sitting in honors biology or honors chemistry or AP biology, and some students came in for the physics class. It was around this time last year. And they did a little presentation. They told you about the physics classes, they did a little demo, they gave you some information, some handouts about the physics classes. They basically bamboozled you into taking this class. Well, guess what? You're going to do the same. Oh, that's it. Logic. It's an opportunity.
Semester at like 45 or something.
Was it 20? How much was it last?
25. We almost have on. I think another 5 or 6.
Yep. So let me read this to you. So in an effort to promote the physics courses here at Valley, I'm asking for the help of students in each of my classes. I would ask a trio of physics students to visit the Honors Chem, Honors Bio, and AP Bio classes in order to conduct a short presentation. Physics AV students should visit Honors Biology. You guys, basically, I want to visit Honors Chemistry and or AP Bio. My AP kids, I want them to visit AP Bio. Each participating student will receive 15 points of extra credit. One presentation will be made per class, that is, per class that you actually have to really visit. And only one presentation can be made by each trio of students. So each trio is just going to do this one time. The presentation will occur at the end of the class period, with the exception of Ms. Beckey's classes. She prefers that students come in at the beginning of the period. Okay, so in a particular class, you basically will just do the following. You're going to be giving the students handouts, the ones that you got last year, for example, that thoroughly explain each of the physics courses, as well as my independent study, astronomy, AP course. Each trio of students will give an overview of the physics courses that includes the following: brief description of the goals of the class, importance of the class when aiming for acceptance into a competitive college, and what you may have personally gained from the class. Your presentation should be at most about 5 minutes and will include a short demo. Tell the students ultimately to see me if they have any questions. Okay, now the demos that I have chosen for students to do in these presentations have been chosen for the ooh-ah factor, as well as being easy to transport. Some of the demos that I do for these presentations you actually haven't seen in class yet. You'll see them, for example, during the second semester. So I will instruct you in their use ahead of time. Don't worry. Okay, turn to the back page. Okay, so this grid right here are the 15 classes that I need to have visited. And I'm going to start these presentations, by the way, next week, basically starting on Monday of next week. Over the course of next week, I want to have all 15 of these classes visited. So because 15 classes need to be visited, that means that I need 15 times 3, that's 45 students. Now I have upwards of almost 200 physics students. So then therefore, how am I going to choose the 45 students basically to do this? Well, we're going to hold a raffle. What you want to do is you want to choose a representative for your trio of students. And your trio, by the way, doesn't just have to be students here. In this class, you can cross over into the other classes with your friends in other classes. That's perfectly fine. But choose one student of the 3 to be a representative. Okay, then that student will attend a raffle here on Wednesday, the 10th, at lunch. The raffle will take place at noon sharp. I'm basically going to fill up the 15 total classes, 45 students, on that day. And then the raffle winners will then come back to my room the next day at lunch. That's when I'm going to go over procedures of how we actually do this, the nuts and bolts of what you do, and then you're also going to sign up for which class you're going to try to present to. And then the presentations themselves will take place starting next week. Usually takes about a week or so to get all of them done. Now, if you do not win one of the 15 slots and you do want to participate, in other words, if you're not chosen in the raffle, there will be an alternate means of obtaining the same 15 points of extra credit at the end of the school year. Okay, so if you don't get one of the slots, don't despair. You will still have a chance to get those same 15 points at the end of the semester. Okay? Are there any questions on this?
So, what does this actually do?
What it actually does, it promotes me. It promotes the importance of physics classes. It promotes the importance of the class, and for you guys as students, let's be honest here, when you're aiming for a good competitive college. The counselors do a good job of promoting the classes in this manner, but this is my means of reaching you guys, for example, last year directly, as quickly as I could. So you guys got a handout from me that introduced all of the physics classes. Hopefully you took a look at that handout as you were thinking about signing up for your classes for this year. That's my means of connecting with the younger students before they actually end up in this room. That's kind of how I do it. Okay, last question.
You say that if you don't get into one of these slots, you say we'll be able to obtain another 15 points.
You'll be able to obtain an alternate means of getting the same 15
So
points.
if we do get this,
Well, that's your 15 points, that's it. You can't get another shot at the end of the semester.
Yeah. Also, like, when is this?
Anything else? All right, please put it off to the side. Please take out notes.
I have to go get to look at. Do you know if you have it in the library? No. So you
Two copies of the check, full check. So you
Okay, so last time in class here in chapter 9, you got introduced to the following quantity. Newton himself referred to it as the total quantity of motion, what's called linear momentum, given the letter P, it's mass times velocity. In the situations that we looked at, however, last time in class, even though the momentum of the system was conserved in those situations, we actually never really did any calculations with this quantity. So where do those types of calculations appear? They appear here primarily at the introductory level in chapter 9 with two very important processes that are very similar to each other. And that's within explosions and collisions. As we'll see, these two processes are in fact very similar to each other. With respect to collisions, it turns out that collisions are extremely important in physics. I'll get to that, however, a little bit towards the end of the day today. What I want to do is illustrate how explosions and collisions allow us to develop a conservation equation. Now what we do is just apply that equation, you see in a very similar manner, to the two individual processes. So we want to first develop the conservation equation. As an example, with the carts that I have there on my desk, I'm going to set up a collision. So the carts will collide, for example, by means of these elastic bands between them, and they're just going to bounce off each other essentially like this. The whole time that this happens, for simplicity, we'll assume that it all takes place on a flat, frictionless surface. So this means that the sum of the external forces is going to be equal to 0. Assume sum of external forces Okay, now here's what the situation looks like before the collision and then during the collision and after the collision itself. First of all, before. So before the collision, I have my two carts. Let's say the first cart here has a mass m1, moves to the right-hand side with a velocity v1 naught, the initial velocity of cart number 1. And then I've got the second cart here, m2. Let's say it initially moves to the left, like so, with an initial velocity of v2 naught. And then the collision itself occurs. The collision itself occurs over a very short time interval as the carts are bouncing off one another. So now during the collision, here's m1, and here's m2. They exert internal forces on one another. They're equal and opposite by Newton's third law. But we have, for example, right here, a force on 2 due to 1. And then right here, for example, is a force on 1 due to 2. Note the terminology that is being used here. But these forces are internal forces to the system. They add up to 0 via Newton's third law. Okay, and then after the collision, the carts separate from each other. So then after the collision, for example, the M1 bounced off and now has a final velocity, say, to the left, and then final.
And then the second cart here, M2, bounced off in the opposite direction, and has a V2 final success.
So this so far is just a picture of all that's happening before, during, and after the collision, like so. Okay, now, because the sum of the external forces is equal to 0, once again, this is all on a flat frictionless surface. This then means that from last time in class, the total momentum of the system, that is the momentum of the center of mass, which is equal to the sum of the momenta of the individual pieces, two parts in this case, is equal to a constant. Now, this is a general expression from last time. Specifically, if we're talking about these two carts, then the momentum of the center of mass is equal to the momentum of each cart added together. This quantity is a constant. So what that means is that essentially the total amount of motion, if you will, of the system before the collision is exactly the same as the total amount of motion after the collision. This allows us to come up very easily with a conservation equation. We write that equation in the following way. If the momentum of the system is a constant, then the change in the momentum of that system from before to after the collision, or alternatively from before to after an explosion, which is equal to the change in momentum of the pieces added together, this is equal to 0. So, and then right here is the conservation equation. So if the total amount of momentum, the total amount of motion, it's a nice way of thinking of it, before the collision and after the collision are exactly the same thing, then the change in the momentum of that system is equal to 0. The beauty of this expression here, by the way, is that when we use it, you don't even really have to worry about the center of mass. That is, you just take a look at the individual pieces, the individual carts, and you just total together the final value of mv minus the initial value of mv, where all the pieces set it equal to 0, and then solve for whatever it is that you're looking for. So with a little bit of practice, using the expression is actually pretty easy. The first situations that we look at is we look at explosions first. We look at what is called a one-dimensional explosion, follow that up with a two-dimensional explosion, and then we start to take a look at collisions. So let's begin by taking a look at explosions first. I'll demo all of this with my cards. As you'll see, this is actually very intuitive as to what's going to happen. So two carts explode apart in one dimension. That means that it takes place in a line. Okay, the velocity of the first car after the explosion is 1 meter per second. Then in parts A and B, we'll set up slightly different situations. Then when we eventually get to part C of the problem, we'll understand qualitatively why this is in fact referred to as a one-dimensional explosion. Okay, so picture-wise, what I'm gonna do is say the cart here on your right-hand side is cart number 1. That's the one that after the explosion will have a velocity of 1 meter per second, and then we'll eventually see here what happens with cart number 2. But before I do that, let's develop our conservation equation first. We'll do so by describing everything in the following way. So here are the two objects, M1 and M2, like so initially. They're initially at rest on a flat, frictionless surface. So the initial velocities of both objects, V1 naught is 0 for the first object, and V2 naught is 0 for the second object. Then the objects explode apart. So what we're given is that M1 here has a final velocity like so, V1 final, equal to 1 meter per second. And then M2 over here, presumably, of course, is going to move off in the opposite direction. We'll have to show that, however, directly, and then we'll find its final velocity here, V2 final. And then here's how we do that. Here's how we set up the conservation equation. This is a one-dimensional problem, so I'm just going to drop the vector notation here. And I'm going to write now the conservation equation as the change in momentum of number 1, before to after the explosion, plus the change in momentum of number 2, from before to after the explosion, is equal to 0. The 0 here is the change in the momentum of the center of mass. But I don't even have to worry about the center of mass, I just have to look at the individual pieces. So for object number 1 first, the change in its momentum from before to after the explosion is just the following. We take the final value first, M1 times V1 final, minus the initial value, which is equal to 0, because cart number 1 begins at rest. So I just have final minus initial, like so, for cart number 1. And then just do the same thing for cart number 2. For cart number 2, its final momentum after the explosion is M2 V2 final, minus its initial, which is equal to 0, because cart number 2 begins at rest. So, and then all that we solve for is V2 final. So to solve for V2 final, move this guy to the other side. In doing so, I'll pick up a negative sign. And toss away my zeros as I go. So. And then just divide by M2 here on both sides to get V2 final by itself. So. And now we'll apply it to our situations here in parts A and B. As you'll see, this is here I get 2. So in part A, we're setting the two masses here equal to each other. And that's approximately what I have here in this demonstration. So then therefore, if the two carts are of equal mass and they initially begin at rest here on the table and then explode apart, we're given that this guy here goes off in that direction at 1 meter per second. What do you suppose that this guy is going to do in the opposite direction? It's also going to go out at 1 meter per second, like so. Basically, well, what's happening here is that right now, when they begin at rest, the total momentum of the system is 0. It has to be 0 the whole time, however, if there are no external forces present. So that then means that after they explode apart, this guy's MV in that direction has to exactly cancel out with this guy's MV in this direction, because the total amount is always equal to 0, and that's, of course, exactly what happens, like so. Showing that mathematically here is really easy, because now in my expression, I just set M1 and M2 equal to each other, they cancel each other out, and then therefore V2 final is equal to negative V1 final, that's negative 1 meter per second. We're solving for a velocity here. These are all vectors, not speeds, hence the negative sign for V2 final being to the left-hand side. And then I just change the situation slightly in part B. This is also intuitive, and I'll demo it in just a moment. But it does say that the second cart, M2, is twice as massive as the first. So 2 times M1. So here's how I'll demo it. Okay, here's M1 like so. And then here's M2. I need to make this guy here twice as massive. I'll just do that to do so. And then the objects will explode apart once again. We're still given that this guy here moves off in this direction at 1 meter per second. So if this guy, say, has a mass of 1, and this one has a mass of 2. If this one here has a mass of 1 and goes that way at 1 meter per second, what do you suppose this guy here with a mass of 2 is going to do? It's going to go in this direction with what speed?
Half a meter per second.
The reason why is that this guy's MV, 1 times 1, in that direction, has to cancel out again with this guy's MV, 2 times 1/2, in the opposite direction. such that the total whole time is equal to 0, because remember, everybody here begins at rest. So it just merely looks like that. That guy's speed afterwards was basically twice that of this one here. Okay, showing it mathematically from the expression is easy. Just go into the expression and then set the m2 in the denominator of the expression equal to 2m1. Like so, the m1s here cancel out, and then you're just left with negative 1/2 times the final negative 1/2 per second. The whole time, if we wanted to focus in on it, the center of mass is remaining at rest the entire time, such that the total quantity of momentum, total quantity of motion, if you will, is equal to 0. Okay, then in part C, this is just making sure that we understand why this is in fact a one-dimensional and not, say, a two-dimensional explosion. So here's what's being described. Okay, let's say that I have my two carts once again, like so. They explode apart. Let's say that the first cart, by definition, goes off in the positive x direction, like so. If that occurs, is it possible for the second cart to do something like this? Like have a y component, like so, to its momentum after the explosion? No, because remember that the total has to be 0. So if this guy goes in mv in the positive x direction, this guy has to have the same amount of mv in the negative x direction, such that the two always add up to 0. If this guy here did something like this, and had a y component to its momentum vector, it's not being canceled out by anything associated with that cart. That then violates, of course, conservation of fluid. So this truly is a one-dimensional explosion. For this reason, the answer to the question is no. Okay, that's a one-dimensional case, pretty simple and straightforward. Two-dimensional case is essentially just an extension case. Here's the two-dimensional case. It's a very wordy description for a simple picture. There's a diagram, of course, that goes with this. But we're going to have an object initially at rest on a horizontal frictionless surface that would explode into 3 pieces. And then we're given all the details of 2 of the pieces, and then we basically have to find what happens to the third. So the first piece, after the explosion, will have a mass of 1 kilogram, a speed of 1 meter per second, and it explodes off into the positive x direction. The second piece has a mass of 2 kilograms, a speed of 2 meters per second, kind of making the numbers here easy. It will explode off at a 45-degree angle with respect to the positive x direction. What we're going to then find in part A, I'll show the rest of it here in just a moment, is the velocity of the third piece, assuming that its mass is 3 kilograms. So once again, I'm just kind of making the numbers here easy to work with. 1, 2, 3. All right, so picture-wise, once again, we just have a flat frictionless surface. Then we've got our 3 objects initially stuck together in the center. So let's say that here's M1,
given all this information about all of these pieces. Okay, first of all, their masses. One is 1 kilogram, 2 is 2 kilograms, 3 is 3 kilograms. So obviously, easy numbers in that sense. Okay, all the objects begin at rest. So the initial velocity of number 1 is 0, same thing for number 2, and also for number 3. Okay, and then boom, these guys explode apart. We're given all the details of 2 of the pieces. So the first piece, it says in the problem, explodes along the positive x-axis like so. So right here is the M1 with a final speed of V1 final along the x-axis. We're given that speed, V1 final, is 1 meter per second. Okay, and then the second piece goes off basically at a 45-degree angle, so it does something like this. Like so. So here's the mass M2 with the speed V2 final. We're also given that speed as well, just 2 meters per second. It looks like an easy to understand what it is. And then the angle made with respect to the positive x-axis by this vector here, called theta, is 45 degrees. This is all that's being described in this very wordy description here. It's this little picture. And then we've got this third piece. Okay, using a little bit of mathematical intuition on your part, into which quadrant here on my diagram do you suppose the third piece explodes into? Not the second. Probably the third one. Probably something like this. So now I don't know that for certain. We'll have to verify it. But here's the piece with the mass M3. It has an unknown final speed, V3 final, but we also don't know what its direction is. So then therefore, right here is an angle that is made with respect to the positive x-axis by this V3 final vector. Let's call this angle here phi. That's how we know. Now I'm just kind of intuitively guessing that it's third quadrant here for V3 final. We will have to show that directly. Two things are immediately different in this example, however, as opposed to the previous example. First of all, instead of 2 objects, it's 3 objects. So I'm going to have 3 terms. And this is also a 2-dimensional case. So because it is a 2-dimensional case, we are going to have a vector sign associated with our conservation equation that is for each term. So, and now typically what you'll find here when we introduce 2-dimensional situations to you here in Chapter 9 is instead of grouping everything together into one expression involving I hat and J hat notation, we instead just break everything up into components. We look to see what happens in the x direction first, and then we look to see what happens in the y direction. So first of all, in the x direction, there's some specific notation that you'll see in most introductory textbooks, including your own. In the x direction, my conservation equation above is written in the following way. Change in momentum of number 1 in the x direction. There's a little subscript here, and that of number 2, and that of number 3. Add up all of those changes, set it equals 0 once again. And then we just fill in everything here, term by term. Well, it's just specifically in the x direction to begin. So we begin with object number 1. So for object number 1, because it does explode into the positive x-axis by definition, its final momentum in the x direction after the explosion is just simply m1 times v1 final. And then we subtract from it its initial momentum in the x direction, which is equal to 0 because it begins at rest. Not only is the initial momentum of number 1 in the x direction equal to 0, the initial momentum of all of the objects in all directions is equal to 0 because everybody begins at rest. So all of these terms here, not just in the x direction but in the y direction as well, are all going to be minus 0 for that reason. But first of all, for the first object, the final momentum in the x direction is m1 v1 final, then minus the initial, which is equal to 0. Okay, and then we get to object number 2. So take a look at object number 2's final velocity vector, v2 final. I'll just draw that here off to the side. So here's m2 with that final velocity vector, v2 final. If we examine its components like so, right here is the angle theta equal to 45 degrees on the diagram above. And then this guy's final momentum in the x direction will be its mass m2 multiplied by the x component right here of the v2 final vector. This is v2 final cosine theta. So the final momentum of number 2 in the x direction is m2 v2 final cosine theta, and then minus the initial, which is once again equal to 0, because that object begins at rest. And then lastly is our unknown here, number 3. Once again, let's just take a look at this vector here off to the side. So, this V3 final here for M3, that will have components in terms of this unknown angle phi. We'll have an x component like so, and a y component like so. But when I write down the term here in just a moment, make no assumptions about positive signs or negative signs associated with these components. That will just come out when we ultimately solve the problem. So then therefore, the final momentum of this guy in the x direction is just the mass m3 multiplied by this component here, which is v3 final cosine of the angle phi. And when I write it down, I make no assumptions about positive signs or negative signs. That will come out in the solution. And now here's then what I solve for. I don't solve for v3 final. I don't solve for cosine phi. What I solve for is actually v3 final cosine phi. Because when I solve for that component, I'm solving for this component of the v3 final vector. And then in just a few minutes, all of the cosines that you see here for the x direction, they basically just turn into sines for the y direction, and then we ultimately solve for this component here in the y direction for v3 final. That's the basic idea. Okay, incidentally, there is a cosine term here. I just didn't write it down. For object number 1, if you look at the diagram above, it's the cosine of what angle? Yeah, cosine of 0. Because that guy explodes along the positive x-axis by definition, but cosine of 0 is just equal to 1. Then at this point, we should just do the algebra. So to solve for this term here that I've outlined in green, first of all, take these guys and just move them to the other side. When you do, you pick up some negative signs, so be a little bit careful in the algebra. And I'll do the remainder here in one shot. To get this by itself, I'll now just divide the m3 to the other side. So after you do the algebra here, just doing it in one shot, please. Okay, when we plug in, everything's in degree mode on our calculator. It's typically how you're going to see things done here for momentum. So I'm now going to just have the following. So first of all, -1 times 1. So this might be the numbers easy. Or -2 times 2 times cosine of 45. And then divided by 3 kilograms here. And I end up with about -1.28 meters per second. So the negative sign means, of course, that this component here points to the left. The size of it is 1.28 meters per second. And then we just set this up in the y direction. And as I said a few minutes ago, really the only thing that changes are all the cosines here just turn into sines. So in the y direction then, it just looks like the following. Once again, some notation here to kind of start. So the conservation equation, written in terms of the y direction, you'll see it here in the following way. So change in momentum of number 1 in the y direction, so there's a subscript. Number 2, and number 3. And then we just fill in all of our terms. Once again, when we do final minus initial for each of these terms, all of them are going to be -0 because once again, everybody begins at rest. So take a look at object number 1 first. If you look at the diagram above, however, what is actually the final momentum of number 1 in the y direction equal to? Yeah, it's 0, because he explodes along the positive x-axis by definition. Or you could think of it as m1 v1 final times the sine of what angle? What angle is made by this guy's vector with respect to the positive x-axis? 0, and sine of 0 is 0. So the first term here is 0 minus 0. This is the final momentum. This is the initial momentum of number 1 in the y direction. And then for number 2, jumping back to the vector here. For number 2, this guy's final momentum in the y direction will be m2 multiplied by the v2 final sine theta, and then minus the initial, which is 0, it begins at rest as well. So, and then lastly, for the unknown, number 3, the final momentum in the y direction, using my basic diagram here, that's going to be m3 multiplied by the y component of v3 final, That's this guy here, is V3 final sine phi. Once again, when I write it down, however, no assumptions about positive signs or negative signs. That comes out in the solution in just a few moments. Minus 0, once again, expressed. And then right here is what we solve for. We solve for V3 final sine phi. That gives us the y component of the V3 final. So to do that, just move this guy here to the other side. When I do, I'll pick up a negative sign, and then I'll just divide by 3. So if you do this couple of minor steps here in one shot, that's so, and now we just plug in. So in the numerator, negative 2 times 2 times sine of 45, so making the numbers easy to work with. Then divide by n3, which is 3 kilograms. This comes out to be another negative number, no surprise, negative 0.94 meters per second. So that's the size of this component right here. But because both the x and y components are negative numbers, this means, of course, that V3 final is into the third quadrant. So in component form, then, we would write the answer to part A in the following way. So V3 final as a vector would be negative 1.28 I hat, and then minus 0.94 j. So in terms of meters per second. So yeah, once again, this is very intuitive. It is, however, a little bit tedious, as you can see, with respect to the notation that is used, but it's easy enough to calculate what it is. We look at it accurately. I'm actually going to in just a moment, because briefly there's a few more details here to look at. Let's just take a quick look at the energy situation involving this. This is part B. And then we'll also briefly understand exactly why this is, in fact, a two-dimensional explosion, why it's referred to that. Okay, says now in part B, just a quick calculation here of how much energy was released in the explosion. Well, just think of it this way. We start off with some sort of potential energy, whether it be spring potential energy associated with these carts like so, chemical potential energy when talking about chemical explosive, whatever. And then what happens to that potential energy? Well, it just gets transformed into the kinetic energy of all the pieces. So this then means that the energy that's released in the explosion is just the total kinetic energy of all the pieces after the explosion added together. So we can think of that then very simply as the energy E as being equal to the kinetic energy of number 1 plus the kinetic energy of number 2 plus the kinetic energy of number 3. And then we just calculate it all out. We calculate out all the 1/2 mv squares. So for object number 1, it would be 1/2 m1 v1 final squared. For object number 2, it would be 1/2 m2 v2 final squared. And then lastly, for object number 3, 1/2 m3 v3 final squared like so. But remember that kinetic energy is not in terms of velocity, it's in terms of speeds. So yeah, I'm sorry, whoever it was that mentioned a moment ago, do we have to do Pythagorean theorem here to find v3 final as a speed? Yes, if we are going to do part B of the problem. So just very quickly here, doing a little bit of Pythagorean theorem. Numbers, 1.28 squared plus 1.4 squared, square root of that. So V3 final's speed, using Pythagorean theorem, is about 1.6 meters per second. That's the number that then has to go in here to do this kinetic energy calculation. Nothing cancels out here or anything like that. We just add everything together, and we get some amount of joules. So for object number 1, it's 1/2 times 1 times 1 squared, which is 10. And then for the middle object here is 1/2 times 2, which cancels out, times 2 squared, which is an additional 4. And then lastly, 1/2 times 3 times 1.6 squared. So 1/2 times 3 times 1.6 squared. This comes out to be about 8.34 joules. Yes, with the big yawn. And then lastly, it says, can an object explode into 3 pieces in 3 dimensions? This is where, like in the last example, we're just understanding why this is in fact what's called a 2-dimensional explosion. Now, if I threw a grenade here in this room and it detonated, and it detonated into 3 pieces, of course it's in 3 dimensions here in this room. But the momentum vectors of the 3 pieces, the instant after the explosion, are all coplanar. It's only a 2-dimensional situation. The reason for that is as follows. Let's think of it in terms of 3 objects, say like so. Let's say these 3 guys explode apart. Let's say by definition, the 2 carts explode into the XY plane, like so. Is it then possible for the 3rd piece to explode like this, for example, where it has a Z component to its momentum vector? No, because remember that the total to begin with is 0. So then therefore, if these guys explode off into the XY plane, this one will also have to explode off into the XY plane, such that when you total up all the momentum vectors, they all cancel each other out. If this guy exploded into a 3rd dimension like so, there would be nothing to cancel out his Z component to the momentum, because these guys are in the XY plane. So that's why this is referred to as a 2-dimensional explosion. The 3 momentum vectors after the explosion are coplanar. So therefore, at a minimum, how many pieces does an object have to explode into for you to have truly a 3-dimensional explosion? Not 2, 4. That's right. Don't worry, we're not going to do the 3-dimensional explosion. It's a mess. Okay, let's take a short break. There it is.
Your back is really good. I was thinking about it. I was thinking about it.
It's so bad. We have where it takes off. For a while, it was like really ending.
Yeah.
I don't know if I'm getting that.
What do you guys think? Boring game? Denver's defense was great.
Yeah, I mean, yeah, it was spectacular, but
It was not exciting at all.
it was an awful game, dude. Cam Newton turned into an amateur in minutes. He had like a mental breakdown or something like that.
Well, he's young, impetuous, not very well disciplined at all.
Were you rooting for?
Yeah, it showed. I wanted to shut. It's so sad. I mean, Peyton Manning is
Peyton Manning's likable though, so I'm glad to kind of see him going on.
yeah, exactly. He's 200 to win. I mean, that's great. I mean, it was sad. I mean, even the O-line for the Panthers just disintegrated.
Well, good defense is going to beat good offense any day of the week.
You're so soft.
Just because like I wanted to see it.
Mid-game.
It was a strong.
Yeah, mid-game, Jordan Ariel met with me that the Panthers would win, and I won
Yo,
20
hold on a
bucks.
second. I gotta talk to Howard. Mr. Howard?
Think about that. Bond they were running at. What would you do? What would you do?
Recently, I got honestly get to the playoffs. You have to win the round. See that interception that right after. Yeah, his brother was mad, bro. Everybody was so happy.
He was like, now he's even. He's like, now I'm not the pick.
Hayden's better than him. The only thing that he had over him was the Super Bowl. So now he has nothing over him. Hayden's better than him in everything. Hayden would have had more.
There's just like send me an email and I'll talk to him. He's pretty young.
Mr. Strauss kind of molested.
You could say that.
And just like none of that is
Mr. Strauss. He's like, integrated science. He leads academia. This morning, I didn't have it. It's not like I forgot. And he took it really personally, and like I told him, I was like, went off. It's like, I want you to read each name, ubiquitously, and like right in front of my girlfriend. I'm just like, seriously? Yeah, so rumor, I mean, like,
Everybody who teaches that class has problems.
yeah, they're useless for teachers. They're teaching a class that's not it literally doesn't happen. I don't know, like, he just wants to know things like super like an email saying like, hey, I didn't hear that call me out of the blue. Like, I was walking under glass and it comes up to me, yes. While I'm walking over there, I heard you were 6 feet. He's like, mate, you told me you had it. I was like, I told you I thought I had it. Unfortunately, I did not. And he was just like, he was so aggressive. I was just like, dude, this can happen at another time. You
Should have done something. Wait, why does he care so much?
Why does he care so much?
Wait,
Because the dude has issues.
what's his name?
Mr. Strauss.
I thought Deca was run.
Academic.
Academic. I thought that's run by that guy. The post on short guy. I thought that always for me.
Oh, really?
I thought that's who ran.
Oh, are you talking about Colado?
Yeah,
You're thinking of Deca.
Oh, so Deca is different from
business.
Academic.
Academic is academic decathlon. Deca is the business. It was just like, yeah, like I said,
That's so weird, bro.
it's just like, it was just like, that's not how I want it.
Should have decked him out.
blow your clock, just like, don't fuck with
Yeah, just flash like, not right now.
Like, what's that game, bro?
He was just like, I don't know, it was like, because we're all such a casual age, like, I was like, hey, what's going on, man? And he's like, what'd you just call me? I was like, man, what's going on? And he's like, you call me Mr. Schwartz. I'll call you a bitch.
No, it's like you pull out like your out of your pocket, like you're leaving there. You're just like, well, but I'll fuck your face. Actually, I'm probably pretty.
I didn't hear your marine biology.
Like, it was really nice, like, dating, like,
What a beast guy. Where you get that rumor from? Mr. Strauss.
I heard that when I was in
Well, let's go.
I know
didn't know that he was here.
Do you know Olivia School? Yeah, she worked at
I just have to go.
All right, everybody, please take a seat.
Like, she told me that.
But her? Well, they have all people.
I really like her. She's kind of intense.
She's pretentious.
She's very
Okay,
intense.
before we actually get to
Kinda hates
situations
that.
involving collisions, quantitative examples, laboratory exercises, etc., what I actually want to do for the remainder of the period today is kind of diverge a little bit and give you an understanding as to why collisions are so important as a process in physics. Extremely important process. The reason why it's so important is because experimentally speaking, it's kind of the only game in town. It's the only means that we really know of exploring the nature of matter at the smallest of scales. The idea is basically to take matter and smash it together at really high speed, at really high energy, as we say. Because the higher the energy that you smash stuff together, the smaller and smaller the pieces are that come out in the collision itself. So we literally explore the nature of reality itself
the nature of matter at the smallest of scales by basically smashing matter together at extremely high speeds. This idea of doing this, trying to study the universe in this manner, definitely lacks a certain elegance. So somebody once compared it to like trying to learn about music by taking a piano and throwing it down a flight of stairs. I love that analogy. But experimentally speaking, it's kind of the only game in town. So experimentally, all it means we have explore the inner constituents of matter. Smallest of scales. Is to smash matter together at extremely high energies. In doing so, by basically exploring the universe at the smallest of scales, you're studying the nature of reality itself. So this definitely sounds like an inelegant way of doing things, study the nature of the universe by smashing things together, but it's really the only game in town. The idea, in terms of an experiment, is actually quite old. It dates back now more than a century to an experiment that everybody here in this room has heard of. And this is in 1911, the very famous Rutherford gold foil experiment. So you may have studied it briefly, for example, in chemistry class or integrated science. But the Rutherford gold foil experiment was kind of the first experiment of its kind. It was actually a collision experiment. And it kind of went something like this, if you recall some of the basic details. I have a slide or two here to help us recall them. All right, Ernest Rutherford, by the way, at the time was in his 30s. Here's a nice picture of him. He was actually a New Zealander living in Great Britain at the time. And he performed his famous experiment in 1911. In doing so, he discovers, essentially as an experimental means, that collisions provides the best means of probing the inner constituents of matter. Okay, now here's kind of the basic setup of his rather simple and straightforward experiment. Okay, what he does right here is he takes a chunk of the newly discovered radioactive element, uranium. He basically surrounds it in a lead box, except for a hole, which is here off to the side. So he has a source here, as is sometimes referred to as. He's got this chunk of uranium. At the time, uranium had just been newly discovered, and it naturally undergoes the process through nuclear fission, if you recall, of what is called radioactive decay. Now, at the time, the process of radioactive decay was not understood. That understanding didn't come until much later on. But what they did discover about uranium, as uranium breaks apart into smaller and smaller elements, smaller and smaller nuclei, is that the unstable uranium nucleus naturally emits positively charged, rather energetic particles. They didn't understand the nature of the particles themselves, but they could make some basic measurements. They could measure, for example, that they had a positive electric charge and they were moving fairly quickly. The way that Rutherford began to think of them is he began to think of the uranium, for example, as a rifle, and you're then shooting from your rifle these positively charged bullets. So we've got here these positively charged particles, like so, which are energetic. They're moving rather quickly. They're being naturally emitted from the uranium as the uranium now know today, by the way, the exact nature of these particles. They were at the time called alpha particles. We still call them that today, by the way. A little bit later on next week, I'll actually show you in a demonstration some alpha particles. But alpha particles, we understand today, are actually helium 4 nuclei. 2 protons and 2 neutrons that are bonded together. And so Rutherford's basic idea is like, okay, I'm going to take these energetically charged, positively charged bullets, if you will, and shoot them at a target. The target was his very famous thin gold foil. Now, why did he use gold? Well, besides gold being very pretty, it's also very soft. It's very malleable. This is why it appears in jewelry all the time, because you can easily shape it. Even more than 100 years ago, it was possible for us technologically to take gold and machine it into really thin sheets. And it truly was really thin. It was actually only a few hundred atoms thick. Once again, think of a nice analogy that Rutherford himself used. It's like taking these positively charged bullets from a high-powered rifle and shooting those bullets at tissue paper. And if you do that, very simply, what would you expect to see happen? What will all the bullets do? Yeah, they'll go straight through. So, and for the most part, that's exactly what happened. These bullets here would go through the thin gold foil as if nothing was even there. And how did he know that? Well, that's the semicircular ring that you see on the diagram. I'm just going to draw it right here, like so. But that semicircular ring that you see on the diagram here is an example of what is called a fluorescent screen. I'll show you one in just a few moments. The screen is coated with a chemical compound called zinc sulfide in this case. When charged particles strike the zinc sulfide, it fluoresces. It gives off a flashing light. Like so. So you can literally see the effects of the particles going through the target, the thin gold foil, and striking the screen here off to the side. Now, before I go any further, let me actually show you an example of one of these things. I'm going to do so using this device right here. This right here is a very distant, primitive ancestor of an old tube type of television. Why is the TV sometimes nicknamed the tube? Because the old tube-style televisions had inside multiple examples of this. This is what is called a cathode ray tube. The way the cathode ray tube works is actually quite simple. Basically, all that it consists of are 2 pieces of metal, these 2 spikes that you see here within the glass, pointing at each other like so. And then what I'm going to do in just a moment is I'm going to use this transformer box, as it's called, to create a really high voltage on either side of the tube. Think of a voltage as like a really steep hill. That hill is so steep that it's actually literally able to tear electrons out of one of the spikes of metal. The electrons then fall down the tube towards the other spike of metal. But when they're falling through the tube, intervening in their path is a screen right here that is coated with the chemical compound zinc sulfide. Zinc sulfide fluoresces when it is struck by a charged particle, such as an electron, in this case of this demonstration. So let me just then show it to you. Don't try this at home. See what it makes. This transformer box, by the way, is able to create a voltage here on either side of the tube that's in the neighborhood of like 15 or 20,000 volts, something like that. And there are exposed wires here, so you have to be extremely careful. See all these exposed wires. So,
How old is that transformer
it's
box?
probably older than I am. Okay, and then turning it on. So. So the light that you're seeing here is the fluorescence, as it's called, of the electrons as they strike the screen. So it's of course not the individual electrons. Those are way too small to see, but you're seeing their effect. Okay, now magnets exert forces on charged particles. This right here is an extremely strong rare earth magnet. And watch what happens to the particle beam here when I bring it rather close to the tube like so. You can see that the beam is being deflected. So magnets exert forces on charged particles. That will be a little bit important later on when I get back to my discussion here. Before I do, however, how is this related to television? Well, the way that old tube-style televisions work is by having multiple cathode ray tubes inside, multiple beams of electrons. And then what you do is you use magnets to steer those beams around such that the beams then strike a screen. When you do this with multiple electron beams, then on the screen forms a picture. That's the basic idea of how an old tube-style television works. This right here is a very primitive ancestor of that. So suffice it to say, getting back to the Rutherford experiment here, he could see where the charged particles were going, that semicircular ring, by placing a screen around the apparatus. And now, as I said a few minutes ago, for the most part, this right here is exactly what happened. Basically, more than 99% of the time, he would fire these bullets at the thin gold foil, and they would just go right through. However, less than 1% of the time, something else happened. It would be like taking your rifle, firing it at tissue paper, and less than 1% of the time, a bullet would bounce off the tissue paper and hit you in the face. It would do something like this. Like so, there would be apparently a collision that occurs deep within the atoms of the gold as these charged particles here strike the gold foil. This happened less than 1% of the time. By working out the mathematical details of these collisions, Rutherford reached immediately three conclusions. Three conclusions about atomic structure. Three conclusions from the mathematical details, from the details of the collisions. First of those details is that whatever it was that was being struck within the atoms of the gold, the target, if you will, it had to be positively charged. The reason why is because it was repelling these positively charged bullets with positively charged alpha. So the target was positively charged. And then secondly, compared to the overall volume of the atom, the target, whatever was being hit here within the atom itself basically has to be mostly empty space. The target itself has to be extremely tiny. We know that because 99% of the time, these guys go right through the gold foil as if there's nothing even there. So the target itself is tiny. If you work out the math of all of this, the way that it follows, as a nice analogy, is the following. Imagine that the entire atom, for example, is the quad outside. If the target is then being struck within the atom itself, that target would be the size of about a grain of rice placed on the middle of the lawn, outside on the quad, if the quad itself was the overall atom. So this is how we know that the atom is mostly empty space. And the target that's being struck in this manner is extremely tiny compared to the overall volume. And then lastly, third, the target is massive. Now, when I say the word massive here, I mean in terms of the overall mass of the atom. The overall mass of the entire atom, if you think of it as the quad, is that little tiny grain of rice that is being struck in this manner. That's what I mean when I say the word massive. Okay, pretty obviously, what am I describing the discovery of about atomic structure with these conclusions? This is what? Yeah, this is the atomic nucleus. But in discovering the atomic nucleus, atomic structure in this manner, by doing a collision experiment, Rutherford kind of hits upon the answer of how we should proceed. That is, in order to explore the inner constituents of matter, we should smash matter together and then look at the collisions that occur. When Rutherford did his original experiment, it was done on a very small scale. It was done at very low energies, just the energy of the particles themselves being emitted from the uranium. It all basically just took place on a tabletop. It was no bigger than the table here in my classroom. Over the course of the next 20 years or so, in the decades leading up to the Second World War, the experiments that were done like this that succeeded Rutherford were all done in much the same way. That is, they took place kind of on a small scale, at relatively low energies,
They did start to use magnets to accelerate particles to higher and higher energies, but it was all still done in a simple laboratory setting, such as sitting here on this table. But during the 1920s and the 1930s, it was these experiments that led to our understanding of how atomic nuclei are structured. So if you recall, what are the two particles that make up atomic nuclei? Protons and neutrons. Protons and neutrons were discovered by doing these types of an experiment. In addition to that, the basic layout of the periodic table. Why the periodic table is laid out the way it is determined by the atomic nucleus. The most important number when talking about an element, in other words, what makes the element, is the number of protons, what's referred to as the atomic number. So in doing these types of experiments, we discovered, for example, that all hydrogen is hydrogen because it has one proton in the nucleus. All helium is helium because it has two protons in the nucleus, and so on. You can think of, by the way, the periodic table as being discovered experimentally by chemists in the 19th century, but in the 20th century, doing these types of experiments, physicists actually derived it, why the periodic table is structured the way it is. So we discovered all those details by doing these types of collision experiments. We also discovered, for example, all the details about nuclear fission, where atomic nuclei break apart, and nuclear fusion, where they come together through these experiments as well. The strong nuclear force, which describes how the nucleons, protons and neutrons come together, was discovered in these experiments. The other nuclear force, called the weak nuclear force, which describes radioactive decay, all of that was discovered in these types of experiments as well. We discovered that elements come in some different varieties sometimes, what are referred to as isotopes. Nicole, please put your phone down. For example, in the case of hydrogen, there are actually three types of hydrogen. Most of the hydrogen in the universe is what's just called hydrogen 1, where it's just one proton in the nucleus. But there's a small percentage of what's called hydrogen 2, one proton and one neutron, and an even smaller percentage of what's called hydrogen 3, one proton and two neutrons. So those details involving isotopes was discovered by doing these experiments as well. That's summarized here very nicely, simply on this slide. So experiments performed prior to the Second World War led to our understanding of protons, neutrons, basically out of the periodic table, and of isotopes. Once again, this is all done on a pretty small scale. Some higher and higher energies were being reached by using magnets to accelerate the particles, but it was all still pretty small. And then we get to this gentleman right here. This was an American physicist named Edwin Lawrence. Lawrence Livermore National Laboratory is named after him in part. Lawrence was the name. Lawrence invents a particular type of particle accelerator that is still used today. It's called a cyclotron. The basic idea of a cyclotron is pretty simple. It basically consists of a circular track. You then line the track with magnets. This then allows you to accelerate charged particles to higher and higher speeds, greater and greater energies. And then what you do is you either divert the beam of particles off to the side and slam it into a stationary target, or you could alternatively set it up where you have beams actually going in opposite directions through the cyclotron. And then at just the right moment, you bring the beams together such that the particles collide at extremely high energies. He invents this device. The first one that he invented, you can see here from the picture, basically fit in the palm of his hand. Then the Second World War happened. The United States and the Allies won the war because of two inventions. Two inventions that came out of pure physics research. I don't care about tactics, I don't care about strategy. It was two inventions that won the war. That came out of pure physics research. The first was radar. Radar allowed the British to win the Battle of Britain in 1942. The reason why they were able to win is because you can see the Nazis' planes coming across the English Channel well before they got there. And they would then have time to set up their defenses. This ultimately prevented the Nazis from invading Great Britain. If the Nazis invaded Great Britain, the outcome of the Second World War could have been a lot different. Because in the spring of 1942, this is before the United States made it to Europe. In other words, Britain basically stood alone. France had already fallen, the Polish had fallen, etc. The only thing left for Nazi Germany to conquer at the time was Great Britain. If they had a chance to invade Great Britain, we may not have been sitting here in this classroom today. Basically, the British won that battle because they had radar. And then secondly, of course, was the invention of atomic weapons, which came from our knowledge of nuclear fission. There is no controversy about the atomic bombings of Hiroshima and Nagasaki at the end of the Second World War. That is not controversial. The reason why is because if we didn't use the atomic weapons in August of 1945, the United States would have had to invade the home islands of Japan in the spring of 1946. And millions of people would have died had that undergone what actually happened. So because we did use atomic weapons at the end of the Second World War, that basically ended the war quickly. Did not have to do an invasion in the spring of 46, which was what was actually originally planned. So because the United States and its allies won the war strategically from these two inventions, the race was on as soon as the Second World War ended and the Cold War began. The United States and its allies, the Soviet Union on the other side, began to dump huge amounts of money, invest huge amounts of money into pure scientific research because of the obvious technological and strategic rewards that you can gain from that. So take a look once again here at Lawrence's cyclotron. Fit in the palm of his hand. This photograph was taken around 1931 or 1932, something like that. And now compare that to this cyclotron here that was built after the Second World War in the late 1940s. This cyclotron, which no longer exists, by the way, was housed at the University of California at Berkeley. It was called Bevitron. The BeV stands for billions of electron volts. The metric SI unit of energy when talking about subatomic particles is not the joule. Instead, we use something else called the electron volt. This particular machine, the cyclotron that's very large as you can see, was capable of accelerating charged particles up to energies of billions of electron volts. The gray slats that you see here, by the way, in the photograph, those are the individual magnets which then accelerate the charged particles to extremely high energies. This machine was basically in operation for about 30 years, from the 1940s to the 1970s, and it led to our understanding and the development of what is called the Standard Model of Particle Physics. Physics today is two things. There's first of all our current understanding of gravity, which is Einstein's theory of general relativity. I will instruct you as to exactly what that is at the end of the year. General relativity perfectly explains the universe at the largest of scales. It explains the expansion of the universe. It explains how galaxies rotate, for example. But then, next to that, is another theory, what's called the Standard Model of Particle Physics. That's our understanding of the small, the other three forces: electromagnetism, strong nuclear force, and the weak nuclear force. The Standard Model of Particle Physics perfectly explains nuclear fission. It perfectly explains nuclear fusion. It perfectly explains its realm of the universe. But the two theories are mutually incompatible. They don't fit together mathematically. This means that you can't use general relativity, for example, to explain nuclear fusion. You can't use the mathematics of the Standard Model to explain the rotations of galaxies. The two theories don't fit together. They perfectly explain their different realms of the universe, but they're mutually incompatible. What that means is that there's something else underneath. There's something else underneath that brings the two theories of physics today into a single cohesive framework, a final theory of physics that brings the four forces together as one. This is where physics is today. It's looking for that final theory. How many of you have ever heard of something called string theory? Okay, a bunch of you have. String theory right now is a guess. It's our best mathematical guess that we know of, at least, of taking general relativity and the Standard Model and fitting it together as one. The current generation of particle accelerators is looking for that final theory. So back in the 1940s to the 1970s, this particular machine was instrumental in our development of our understanding of three forces that exist in nature. When you see a depiction of the Standard Model of Particle Physics, you'll usually see something that looks like this. You'll see some sort of colorful diagram. The particles have some whimsical names associated with them. You'll see them grouped together according to their mathematical properties. And it's how these particles, which come out during the collisions themselves, how these particles interact with each other, that's then what we see as electromagnetism. It's what we see as the strong nuclear force
and so on. This theory, by the way, is so successful in explaining these forces that we could actually also use it to explain the entire history of the universe from this point all the way back to a time of only 10 to the minus 43 seconds after the moment of creation itself. It's so successful with the theory, it can actually explain that. How we know that is a really long story. Now, with respect to particle accelerators, let me show you some examples of them. There are essentially two basic designs. There's first of all what's called a linear accelerator, which is kind of like Rutherford's old experiment on steroids. Basically what you do is you take your particles, you accelerate them down a linear track, and then you slam them into a stationary target. The longer your accelerator, the higher the energies you can reach. So the longest linear accelerator in the world is actually here in California. It's up at Stanford University. It's called the SLAC here for obvious reasons. From this aerial photograph, the actual tunnel itself is 2 miles long. This type of a setup is useful for slamming particles into really heavy atomic nuclei, as is being described here. Then over in Massachusetts, at the Brookhaven National Laboratory, this right here is called a RHIC, the Relativistic Heavy Ion Collider. It actually uses a combination of a linear accelerator here and a cyclotron to perform different various types of experiments. It's useful design in doing certain things. Okay, this right here is the largest cyclotron in the United States. It's in suburban Chicago at a place called Fermilab. Fermilab is named after Enrico Fermi, who is an Italian physicist who lived and worked at the University of Chicago. This is kind of like the successor to the Bevatron. It's 1,000 times more powerful. This is why the Bevatron was eventually dismantled at the University of California. This is called Tevatron, which stands for trillions of electron volts. So it's basically 1,000 times more powerful. The main cyclotron ring, which is actually underground, about 50 feet or so below that path, is 4 miles in circumference. Okay, this right here is what you would actually see in the tunnel itself. This pipe right here is where the beams of particles are, and then blue above and red below, these guys are the magnets, which then accelerate the particles to higher and higher speeds. The actual collisions themselves take place at specific locations along the cyclotron, inside of massive devices that are referred to just generically as detectors. So what they do at the locations of the detectors is they then steer the beams into each other, or they steer the beam into a stationary target for the cyclotron experiments that are being done. This was, once again, the largest accelerator that was built in the United States. The Europeans had their own version of the Tevatron from the 1970s up until the 1990s. It was called the Large Electron Positron Collider. It was basically a twin, if you will, of the Tevatron in the United States. However, the Europeans made a decision in the 1990s to decommission that particular machine, and in its place, they then built what is today the most powerful cyclotron that we have built worldwide. And that's what's called the Large Hadron Collider. The main cyclotron ring right here from this aerial photograph is 27 kilometers in circumference. How many of you have heard of this laboratory called CERN? A few of you have. It's actually a French acronym. It basically stands for the Center of Nuclear Energy Research. CERN, it turns out, is actually administered not by just the Europeans, but it truly is a global, worldwide effort to do something like this. You'll kind of see why as I go forward here in the slides. The internet, by the way, was created at CERN in the late 1970s. The original reason why the internet was built was to take the data from these old LEP experiments and then send the data packets out around the world using a computer network to various universities around the world. This was the first application of the internet. Today's internet is actually built upon that network. And then also the internet in part dates back to a US DoD project from the 1970s as well. Okay, this is the Large Hadron Collider. If you go underneath the accelerator ring in the tunnel itself, this is what you would see. So the beam itself is inside this pipe. Okay, the blue rings that you see here are the magnets which accelerate the particles to extremely high speeds. As you can see from the slide, the actual beam of particles is less than the width of a human hair. And what they actually do is they arrange the beam of particles in long needles like so. They then accelerate them up to speeds of more than 99% the speed of light. And they do this with beams in opposing directions. They bring them together such that they smash together at the detectors, or they then steer the beam into a stationary target. Okay, right now, the LHC is being run at full strength. For about the last year or so, they've been gathering data of collisions at essentially full strength, what is being called Run 2. The energies being reached by the collisions now are far above anything that's been previously attained. The results of all of this of Run 2 are expected later this year. Everybody's got their fingers crossed that this machine is finally going to look beyond the standard model of particle physics, point the way towards a final theory. That's what everybody is hoping. Okay, this is an example of one of the detectors. It's basically a large collection of magnets. That's essentially what you're seeing right here. This is called the compact muon solenoid. It's in part actually run by UCLA. Now, when I say that the LHC is at CERN and it sounds like it's a European machine, that's not quite the case. After the United States built the Tevatron, in the 1990s, there was an attempt by the United States to build a much larger accelerator. It was then called the SSC. SSC stood for Superconducting Super Collider. It was going to be built in Texas. As soon as the United States started building it, however, what we discovered is that it was massively expensive. And so ultimately the project was killed. When the project was killed, everybody basically pooled their resources. The Europeans, the United States, China, Japan, Canada, Australia, et cetera, et cetera. Everybody basically pooled their resources to rip out the old LEP at CERN and build in its place the Large Hadron Collider. So the Large Hadron Collider is kind of like a scientific project that is species-wide. It's beyond the ability of a single nation to do something like this, so everybody has basically pooled their resources together to do it. So UCLA, for example, is actually heavily involved in one of the experiments that is being run there. This right here is not really a picture per se of a collision, but it's just kind of a reproduction afterwards based upon the data. But what you're seeing here is essentially opposing beams coming in from opposite sides, smashing together, and then all of this stuff that you see right here, that was all the standard model diagram from earlier in the slides. And then basically what you do mathematically is you use a combination of conservation of momentum and energy to work out all the mathematical details of what happened, for example, prior to the itself. I'm sorry? Yeah, you're doing a very simple version of this. And here's another example of one of the detectors, as they're called. The word ATLAS is an acronym for something. Each individual detector by itself easily costs over $1 billion. Billions of dollars have been invested in the LHC by a number of different countries around the world, once again, all pooling our resources. It truly is a species-wide endeavor to do something like this. Now, I mentioned earlier that right now the LHC is doing what is called Run 2. A couple of years ago, they ran it for the first time, and when they did it at approximately half strength. It immediately led to a discovery in 2012 of what is called the Higgs boson. How many of you have heard of this term, the Higgs boson? Okay, good, a few of you have. So what the hell is the Higgs boson? The Higgs boson was first mathematically predicted to exist by a Scottish physicist named Peter Higgs. It's basically a part of the standard model of particle physics, but it had never been observed in any other collider experiment prior to what happened here in the LHC in the year 2012. Now, what the hell is the Higgs boson? Let's go back to chapter 4 for a moment. Remember inertial mass. The mass of an object essentially describes how difficult it is to change its velocity. The more mass of an object, the harder it is to accelerate. And then we have just used that description of mass and have just kind of gone from there all the way up until this point in class. But at a fundamental level, where does mass actually come from? It comes from the following. Think of it like this. Let's say that us here in this room are what is referred to as the Higgs field. Everybody here is a part of that field. And let's say that all of us here in this room are actually at a party. Let's think of the Higgs field as a party. And then there's a knock at the door.
somebody walks into the party. So I'm sure you guys go to parties all the time. What happens when somebody comes to the door at a party and that person doesn't really have any friends, not very popular or anything like that? What do you guys do? You pretty much ignore that person probably, right? So what that means is that none of you go over there and start to talk to the person. That means that the person has no mass. And now, let's say that somebody comes to the party who's very popular. So Keon comes to the party, and everybody says, "Hi, Keon." And then what does everybody do? You all go over there and you start to talk to Keon. Is it easy for him to walk through the room then? No. The reason why is because you gave him mass. You made it difficult for him to move through the Higgs field. So he's more massive. He didn't walk in with that mass. You guys gave it to him by going to him. That's essentially what the Higgs boson is. It's basically a particle that gives all the other particles mass. That's the easiest way to think of it. So what then actually happened in this experiment in the year 2012? Well, basically what they did is they smashed matter together so hard that it broke off a piece of this room. It broke off a piece of the Higgs field. It broke off a particle that's referred to as the Higgs boson. And that immediately led, of course, to confirming a portion of the Standard Model that had not been previously observed. Nobel Prizes galore. It's hoped that the properties of the Higgs boson will point the way to new physics. There's a little bit more to this. I'm going to get to that, however, in the class next time. This keeps you even with the other classes, so I'm going to stop here. Hey, take a look over here at the agenda board. There's nothing specific due on Wednesday. You definitely want to get a start on the website. If you haven't already done so, then just do it. Okay? These guys?